안녕하세요 여러분, 해리입니다. So in this video, I'm going to talk about functions, which is one of the four most important topics that you have to understand well in order to survive in calculus. So first, we start with the definition. So let's try to understand what function is in mathematics. So in real life, function, basically it means like it's doing a certain task, right? So ability to do a task. Then in mathematics, it's the same. So there should be a certain function, and that means there must be some input to put into this function. And this function is desired to create some outputs of the corresponding input. So one thing that you should know is that there cannot be no output for some input, and there cannot be no input for some output. So what I'm trying to say is that there must be input and output corresponding to each other. Okay? And in mathematics, we can have many to one. So that means for different values of input, we have the same value of output. And we can see this from, for example, quadratic equation or quadratic function. So for example, if we want the output as 1, then we know that input can be either 1 or -1 if the function is y equals to x squared, right? So if y equals to x squared, then if we want the output as 1, that means we have two different values of x, plus and minus 1, right? So many to 1 is possible in functions in mathematics. But what about something like 1 to many, or many to many? All right. And lastly, 1 to 1. So for functions in mathematics, we only consider these two. These are not functions in mathematics. So for example, 1 to many, that means something like this, a graph like that. So or I'll just make a circle. So equation of a circle. So assuming that this center is, for example, like k and with radius r. So you don't have to know the equation of the circle, to be honest, but so that's the equation. So for the function of the equation of the circle, and this is not a function because for a value of x, there exists two different values of y, right? So this case is 1 to many. So this is not a function. And as the same, many to many is not a function either. So only many to 1 or 1 to 1 are defined as functions in mathematics. Then how do we check whether a graph of an equation is a function or not? So we have two tests in functions. So the first test that we learn is called the vertical line test. So what this evaluates is that if you have a sketch of the graph of a certain equation, then just prepare a pen or any like straight thing and scan the entire graph for the specified domain. So what that means is, what it evaluates is that for every value of x indicated by this line, there is only one value of x, right? Right? So this case, this graph passes the vertical line test. That's why this equation is a function. And similarly, something like so if you have learned some piecewise functions, something like that, then again we can try vertical line test to see whether this is a function or not. So using any straight thing, we see that there exists one value for every x, right? And what this means is that it includes this certain point, and this means it does not include this certain point. So for example, if this is 1, then the y value at 1 exists here, but for this one, the y value for when x equals to 1 is not defined. Okay, so that means at this particular point, when x equals to 1, there is one value of y, because this one doesn't have any value. And it's the same for this, okay? So this one is also a function. Then what's not a function, as I said, something that has multiple values of y for a certain value of x. So for example, something like this. So using the vertical line test again, for any value of x, not any, but for specific value of x here, we see that there exists two different y values. So we can define this as one to many, right? So that means this is not a function. 빨간색 펜 있어. So yeah. Then using vertical line tests, we have seen that, so basically using vertical line tests, we can define whether a graph of an equation is a function or not. Then what's the second test? So we have the second test called the horizontal line test, and this is to find a one-to-one function. So in order to be a function, then it has to pass the vertical line test first. And after this test is completed, then we move on to the next test, where we now try horizontally. So horizontal line test. So that means for a certain y value, there must be only one x value. So for this one, it doesn't pass the horizontal line test, because as you can see, at this particular y value, there can be 3 x values, right? So this is certainly not one-to-one. What is one-to-one then? So something like this. Any linear is one-to-one, right? So it passes the vertical line tests, and it passes the horizontal line test as well. And something like a cubic, where it has a point of inflection. So this is also one-to-one, because vertical line test and horizontal line test, there is only one value corresponding to one specific value. Okay, so these are the two tests to find the variety of functions. And this horizontal line test, you will need it for later when you have to do the inverse functions. So yeah, this is the very basic things for functions in mathematics. Then now let's move on to some more mathematical part. Domain and range. So first, what's domain and range? So as I said in the beginning, every function follows this algorithm. So every function, as long as it's function, then there must be an input and there must be an output. Then for this input and output, we have a mathematical term for that, and this input, we call it as domain, and this output, we call it as the range. So if you have seen these words already, domain refers to all possible values for x, and range refers to all possible values for y. So we're going to investigate the domain and range of different functions that we've learned so far. So first, let's start with a linear function, the most basic one. So a linear function is a function in form of mx plus c, where it has a gradient and with a certain point. So for example, let's say we have a linear function like this. Then for every linear function, is there any restriction to x values or y values? And as you can see, the graph keeps on going, right? Going and going. That means it can just go forever, positive infinity, and also positive infinity, and negative infinity, negative infinity. So what does that mean? The domain, which refers to the possible values of x, belongs to real number, because it can be anything, right? So if x can be anything, then we write it like that. So it's a set notation. So this r, it's not IR, it's r. And this refers to the real number, set of real number. And this notation means belong. So x belongs to real number. That means x can be any real number, okay? And as similarly, there's no restriction on range as well. So that means y can be anything. So we can write like this. So y belongs to real numbers as well. Okay, so for every linear functions, unless there is a specified condition to it in the question, the domain and range must be defined like this. Okay. So second, quadratic. So quadratic, as you guys already know, it's in the form of ax squared plus bx plus c, right? So when a is positive, we have a smiling face shape, and when a is negative, it's unhappy face, right? So that means there are two cases of quadratic functions. Either we have a case where a is positive, or a case where a is negative, right? Then let's investigate the domain and range again using the graph. So for finding domain and range, to be honest, if you could sketch the graph, that's the best method to find the domain and range, okay? Don't try to solve that algebraically. Sometimes it's not really easy to see. But anyway, so since for quadratic, I'm pretty sure everyone can sketch it. So let's look for the domain. Is there any restriction from the graph? No, right? Because this graph it keeps on going, right? So that means going in that direction, then x can be anything on positive side. And similarly, this means x can be anything on the negative side. So for domain, it's all real number. And it's the same for this case too, right? So it's negatively ongoing, and that means x can be anything, and x can be, anything on positive side and negative side, right? So for both cases, x can be anything. So x belongs to real number. But what about the range? Do you see any restriction? And we clearly do, because we see that this has a minimum, right? And this has a maximum. So y cannot go beyond this, or y cannot go below this point, right? So the range for quadratic functions, it depends on the vertex, right? And I'm pretty sure you guys all know how to find the vertex very quickly. So we can either we can either complete the square from the given equation and then find the vertex, or you can use the results directly. So the result from completing the square, where if x equals to negative b over 2a, that gives you the x coordinate of the vertex, right? So once you find that, if you put that in, then you have the y value. That means you can have the information of the minimum point or the maximum point. So the range must be this one or above. So it's equal or greater. And for this one, it's equal or less. So for example, let's try a question like this. So let's say y equals to x squared plus 3x. Okay, I don't like odd number here, so let's say 6x plus 8. Okay, so as I said, if you could sketch it, it's very good to sketch, but for this one, as we can see, there is no real roots, right? Because the discriminant is less than 0, so no, actually the discriminant isn't 0, so well, yeah, we can find the roots of it. So oh, sorry, I thought I made a random equation, but turns out that we can just simply factorize it. Yep. So we can we know the roots, so we can sketch it, right? So -2 and -4 and y-intercept, so it looks like that. And you can see that, so this one has a minimum point, right? So that means we have to find the minimum point in order to find the range. So first, domain is simply x can be anything, right? So for range, we have to find the vertex point. So as I said, 2 methods. So either you complete the square or just use the results directly, but completing the square shouldn't be that hard. So I'll just quickly complete the square. So that's how it looks like. So that means at -3 and -1, that's the vertex. Then the range. Now, according to the graph, the range must be greater or equal to -1, right? And when the very first coefficient of x squared is negative, then we know that it's in this shape, so you can possibly sketch the graph and then find the domain and range. So it should be very simple, right? So that's it for the linear and quadratics. Now let's do something else, which are not that simple, like linear and quadratic. So we're going to see the basic trigonometric functions. So let's start with y equals sine x. And you guys should be able to sketch this, right? So just a normal sine x. The period is 2 pi, which is 360 degree, right? Because pi is defined to be 180 degree, right? So that's how the sine graph looks like, and we know that it's from 1 to -1, and it repeats over and over and over again, right? So it just keeps on going. It just keeps on going. So from this, we can see that the domain is real number, right? Because as I said, it just repeats and repeats over, right? That means it goes infinitely positive or infinitely negative. So x can be anything, right? Then what about the range? So as you can see from the graph, every y value lies between -1 and 1, right? So that means y belongs to the set -1 and 1. So this is using the set notation. Or you could also write it like this. So these two are the same thing. Okay? So this is just using the set notation, and this is using inequality that we already know. So yeah, sine x shouldn't be that difficult. Then what about cosine x? So if you have already done some trigonometric functions, then you know that cosine is just a transformed function of cosine, right? So as you can see from sine, if we shift everything to the left, by 90 degree, then we'll have cosine, right? That's how it looks like. So that's where 2 pi is, and that's where pi is, okay? And again, as I said, it's just this cosine graph is just shifted from sine graph, so still it's 1 to negative 1. So the domain and range are the same. Then the thing is tangent. So if you recall the very basic trigonometric identity, tangent equals to sine over cosine, right? Sine over cosine, that means for a certain value of cosine, where for certain values of x, where cosine becomes 0, like 90 degree or 270 degree, tangent is not defined, right? Which means that those two are the asymptotes. And so on and on, right? So that is how the tangent graph looks like. So the domain here, okay, the domain is a bit difficult, so let's just leave it for now. Let's do range first. So range, as you can see, it can reach positive infinity and negative infinity, so that means it can be anything. Right, then the domain is a bit problematic because we see that x cannot be negative pi over 2, and cannot be pi over 2, and cannot be 3 pi over 2. And it's on and on and on, right? Then we must try to come up with a pattern, because we can't just write x cannot be negative pi over 2, x cannot be pi over 2, x cannot be 3 pi over 2, dot dot dot. We cannot write like that, right? So let's try to find the pattern of this. And in fact, all the asymptotes are a multiple of pi over 2, but not every multiple, because this pi here is 2 pi over 2. So that means it's a multiple of pi over 2, but it's multiplied with an odd number. And how do we express odd number using algebra? 2k plus 1, where k is an integer, right? So that means x can be anything except Alright, so it's a bit messy to see, I think, so I'll just write a bit bigger. So x can be anything except the odd multiples of pi over 2, where this k is an integer, so that 2k plus 1 always yields integer. And if you don't want to write it using the set notation, unfortunately it's very hard to write it. It's very hard. So I think it's better to just use the set notation as for tangent, okay? So that's the domain for tangent. So you can see that the graphings are very useful to find the domain and range of certain functions, especially when the function gets more complicated. So for example, sine, cosine, and tangent are certainly more complicated than linear and quadratics. So instead of just, what you can try is that you can try to memorize the basic sketch of sine, cosine, and tangent, and then you can derive the domain and range using the graph. Or you can just memorize the domain and range of sine, cosine, and tangent, because they're not that hard, right? So that's it for the basic trigonometry. And what else do we have? We also have learned log and exponential functions, right? So I'll start with exponential first. So exponential, that means y equals to a to x, right? So we have some different case. So it can be divided into 3 cases. Why? Because first, so it can be divided into these 3 cases. And one thing you can see that a cannot be negative. And why is that? So the base here it must be a constant, and x should be the variable, the independent variable. So then if a is a constant, then let's try to see what happens if the base is negative number. So for example, let's say a is negative 2. Then x there, can that be half? The problem is, can that be half? And the answer is no, right? Because negative 2 to half, that means root negative 2. So negative number inside the square root is not defined in real number, and functions we learn right now, we only consider real numbers. So it's not defined. So we just separate the base into, we define this base as a positive number. Okay, and so for the positive values of a, we have to differentiate into 3 cases, because all the sketches are different. So for example, when a is between 0 and 1, and if we have to sketch y equals a to x, then let's try to see what happens. So for example, let's say a is half. A is half. Then if the power gets bigger and bigger, what do you think it will happen? The y value will get smaller and smaller, and we can clearly find this from, well, you don't really have to use calculator, but in order to save time, I'll just use calculator. So 0.5 squared, that means it's getting, you see that the value gets smaller and smaller as the power gets larger and larger, right? Then what about when the power is negative? So remember, using the exponential property, if the power is negative, then we take the reciprocal. So the reciprocal of half is 2. Then when the power is negative 2, then what does that mean? We are taking the reciprocal of 0.5 squared, and 0.5 squared is 1/4. So the reciprocal of 1/4 will be 4, right? And we can see that as the power gets negatively larger, the value gets bigger. So using that fact, as x gets positively larger, the y value gets very small, and as the x value gets negatively larger, then y gets really large. So it looks like this. And this is the intercept, right, when x equals to 0. And everyone knows that something base to 0, unless the base is 0, is 1, right? And we also be aware that y cannot be 0. So there's a horizontal asymptote, right? Because imagine we have a base, right? And we know that if the base is positive, then no matter what the power is, it cannot go below 0, right? It cannot be negative. And why can't that be 0? Because, so theoretically, using the concept of limit, the limit value when x is positive is 0, but we're not looking for the limit value. And you don't really have to care about limits yet. You will do that in calculus later. So yeah, just remember that the value gets very small and small, but not 0. It will never become 0. So using this, we know that the domain can be anything, right? So the power here can be anything. And the range, what about the range? Range is bigger than 0. And if you want to use a set notation, we can write it like this. So y belongs to 0 to plus infinity. And this means not including. So y cannot be 0, right? 0 is not included, so we use this symbol. Okay? And note that infinity is not a number. It's just a it's not a number, it's just keep divergent. It's getting bigger and bigger and bigger. So we can't have a value equal to infinity because again, infinity is not a number. So we have to put this sign. But if you don't want to use that notation, it's fine to use that. Alright, so the second case when a equals to 1. So a equals to 1, that means y equals to 1 to x. So y equals 1 to x, that means whatever the power is, no matter how many times you multiply 1, the result is 1, right? That means y equals to 1. So that means for this one, x still can be anything, right? But y is just 1. You will not be asked to do this, but just this is important. Okay, just remember that this way of looking at case by case, is very important later for inverse functions. So lastly, when a is positive, and I'm pretty sure, when a is larger than 1, I'm pretty sure you have already seen this in exponential chapter. So it looks like that. And that's it. So for this one, it's the same with this. So y is always positive, and x can be anything. Now log. So if you have learned a bit of log and exponential, then you may have heard that log and exponential are in inverse relationship, and I'll talk about that later, but just note that this a is the same as this a. Okay, so that means a greater than 0 still remains the same. And let's again divide the case for a between 1 and 0, and a equals to 1, and a greater than 1. Right? Then that means, so for the first case, when a is between 0 and 1, what does that look like? So it's a bit hard to tell right now because so for sketching, so at this stage it's very difficult to sketch. Okay, it's very difficult to know the sketch of it unless you learn the inverse function. So I'll just sketch for you. Okay, so this is how it looks like. So we're going to come back to this in inverse function later. So just remember that the log graph when the base is between 0 and 1 looks like this. So as you can see, the domain is now restricted, right? The domain is only the positive side. So x is greater than 0, or using the set notation, x belongs to this set. And y can be anything, right? Y can be anything. And second, right, so for a equals to 1, that means the graph looks like this. And let me ask you one thing. Is this a function? The answer is no. Why? Because this is one to many, right? So remember, let's check for a vertical line test. At this x value, x equals to 1, how many y values are there? Infinitely many, right? So that means this is not a function. So in log function, the base cannot be 1. Okay, very important. Base cannot be 1. And this is for log only, because you can see that for exponential, when the base is 1, it's still a function, right? It still passes the vertical line test, so it's a function, yeah. But for log, when the base is 1, it's not a function. Okay? And lastly, this you guys should already know that looks like this. So this is the x-intercept. So again, like this, x, the domain is positive real number, and y can be any real number. So that's it for log and exponential. Then we have seen quite a lot of functions. So some may think that maybe that is it, but I'm sorry, you have 2 more for SL and IGCSE. And for HL, you have 6 more, where you have to do the reciprocals. So reciprocals of trigonometry and inverse of trigonometries. But so if you're in SL, you don't have to worry about this. That's only for the jobs for HL. So last, rational and irrational. So this one I will not talk in detail, but you need to know the basic form, like in quadratic or linear, or like log and exponential. Okay, so first we start with rational. So what's rational? So where have you heard the word rational? You probably have heard the rational numbers, set of rational numbers, right? And what are the numbers which numbers belong to rational set, the set of rational numbers? Any number that can be expressed into a fraction, right? So that means rational is a function in the fraction form. So where the denominator has the independent variable x. So the very basic form of rational is this. So k here is a constant. So again, we're going to look at 2 different cases where k is positive and where k is negative. Then also, do we have to look for when k equals to 0? No, because if k equals to 0, y equals to 0, it's nothing, right? So let's first look at when k is positive. And I'm pretty sure most of you have seen this already. So first, can x be anything? The answer is no, right? Because the denominator cannot be negative. That means we have a vertical asymptote, x equals to 0. And is that it? Is there any other restriction? Yes, there is, because k is not 0, right? So k is a constant. Then in order for a fraction to equal to 0, I mean, for which case is the fraction, can the fraction be 0? If and only if the numerator is 0. But is the numerator 0? No, right? Because k is a constant, and we already said that k is bigger than 0. So k is not 0. That means y cannot be 0, because fraction cannot be 0 unless the numerator is 0. Okay? So we have another asymptote, y equals to 0, and it's called the horizontal asymptote. So then how do we sketch? So let's see some patterns. So k is a fixed constant, right? So if x is positively large, then what happens to y? So for example, let's say k is so k is a positive number, so let's say k equals to 10. Then let's investigate some different values of x. So let's say x at 2, and x at 4, and x at 10, and x at 1000, and x at 100k. And you see that the value gets smaller and smaller, but can it be 0 or negative? First, it cannot be negative because we only have positive numbers. How can it be negative, right? And second, it cannot be 0 because it gets really, really, really small, but still it's not 0. We can't, as I said, the fraction can only be 0 when the numerator is 0. So it looks like, so we see that it's approaching to 0 when y approaches to 0 when x goes to positive infinity. Then what about when x tends to 0? So using the same case, we said k equals to 10, right? Then let's say x equals to half. Then remember this, if you have a fraction, if you have a number less than 1 in the denominator, then it's taking the reciprocal, so it gets larger, right? And as it gets smaller and smaller and close to 0, we see that the value gets larger, right? So that means it looks like this. And doing the same thing for negative side, so just try some negative values for x. So for example, again, k is 10. So when x is, for example, negative 10, and when x is negative 100, and when x is negative 1000, and we see that the value gets smaller and smaller, but it's just negative. And can it be positive? No, because the denominator is negative, right? But the numerator is positive. So a multiplication or division of one positive and one negative is always negative, and it cannot be 0 either, okay? And it looks like that. Okay, then what's the domain and the range? So we can see that x can be anything but not 0, and y can be anything but not 0. So using the proper set notation, x can be negative infinity to 0, union 0 to positive infinity, and the same for y. So y can be negative infinity to 0, not inclusive, and union 0 to positive infinity. So I'm pretty sure you have already learned the basic set notation. So this union or intersect, right? So union means either this or that, and that's what it means, right? So we're done. Then what about when the case is negative? So that means k is negative. So we can do the same thing, but just flipped around, like in quadratic, right? So when a is positive, it looks like this, but when a is negative, we flip it, right? The same. So everything remains the same except for the general sketch. So again, even if k is negative number, x cannot be 0. And also, since k is still a constant, non-zero constant, that means y cannot be 0. So we have the vertical asymptote and horizontal asymptote, and just flipped like this. That's it. So that's the rational function. So, and the domain and range for this case is also this, okay? Now, last for IGCSE and SL students, irrational. So the basic form of irrational is something like y equals to k times root x, where k is again a non-zero, constant. So similarly, we divide into two cases where k is positive and k is negative. So when k is positive, so we try to sketch root x. Okay, one thing, can x be negative? And very simple, x cannot be negative, right? Because can there be negative number inside the square root? No, that's why x cannot be negative. Then can x be 0? The answer is yes, because 0 squared is 0, right? That means root 0 is 0, right? So it starts from 0, the origin. And what happens as x gets positively larger? Then it looks like this. Okay? Then what about when the case is negative? Again, nothing changed, but just k became negative. So just flipped like this. Then what can we say about the domain and range? So for this one, x is greater or equal to 0 for domain, and y is also greater or equal to 0. But for this one, x is greater or equal to 0, but y is less or equal to 0. So you must put special attention to the very first coefficient, because, okay, root x can only be positive, right? Then if k is positive, then positive times positive, so it's always positive. That's why y has a set of positive numbers. But if k is negative, then root x, no matter what x is, it's positive, right? Root x must be positive. So if k is negative, then negative times positive, that's a negative number, right? So y has a set of negative numbers. And that's it for irrational and rational. And later, you will see a lot of cases, like, for example, sketch this, or sketch like something like this, right? Which is a transformed version of rational and irrational. And for these cases, we're going to do in transformation. So in the next video, okay? So if you learn transformation, then you don't really have to care, like look at these cases differently. You always start from these basics. This base functions, base form, okay? So that's it for the varieties of functions. And now we have to do a bit more. So that's it for domain and range. And now we're going to look at some types of mathematical functions. So not all those like rational or irrational, but more in the category of the function chapter. So majorly you will have to learn two functions. So first, composite function, and second, inverse function. And you'll have to learn identity function as well for SL students, and probably for IGCSE as well, I think. And if you're in HO, then you have to learn several more functions. Not hard, but just some basic types. So for HO, you have to learn even functions, odd functions, and self-inverse functions as well. But so first, I'll focus on SL syllabus. So if you're in HO, you still need to watch this, but just remember to watch the HO ones as well, okay? So first, composite function. So it's also a function, and then as I said, every function has an algorithm, right? Where we have the input, and then we have the output. There is no function where there is no output or no input, okay? Always there must be input and output. And as we just discussed, as I just talked about, input and output, they have a mathematical terms for that, for this. So input we use domain and output we use range. Then what is a composite function? Composite function is a function where input becomes another function, or not necessarily another. Input becomes a function. Or functions. Yeah, let's say functions. Then what does that mean? So if you are a student who is interested in computer science, you may have used a lot of functions, especially some of the recursive functions. So it's basically using that. So recursive function means you put the same function over and over and over again, right? But so recursive function is an example of composite function. So we can think like this. So input can be anything, right? So for example, let's say fx equals to x plus 1, let's say. Then it's a linear function, right? So the domain is all real number and range is all real number 2, right? And so for this one, this is the input, the domain, right? Then what about if we change the input as something like x plus 1, right? What does that mean? So before we go for this, what does this mean? For every input, so what this function means that not just a linear function, but it also means that for every input, we add 1. That's the meaning of this function. Then, for example, if you have a quadratic, let's say, something like this, what does this mean? For every input, you first square it, and you times it by 2, and then you add 3, and you add them all together. Right? That's what it means. So, for example, if you want to devise a function that calculates the, for example, the average of let's say okay, I can't really think of a good example, but for example, let's say you want to devise a machine that doubles your age and add 1. Okay, it's a very stupid example, but anyway, that's the only thing that I can think of. So whenever you have an age, you want to devise a function that doubles the age and then add 3. Then how can we make that function? This, right? So every age here we double it and we add 3. That's just that's the point of using functions. So for all this repeating task, so for example, if you have to find this result for example, when you're 20, when you're 21, when you're 22, and so on, you don't want to calculate like every time, right? So what you can do is that you can devise a function and you just insert that specific value for the age as an input. Okay, so that's what the function is. So that means, what this means is that for every input x plus 1, we add 1. Actually, so since we have used f, I'll just use g. Okay, so that's what it means. X input, for every input we add 1. For every input we add 1. Same thing for this. So for example, if we're looking for gx minus 2, then again, the function gx means you square the input plus you double the input plus 3. Then doing the same thing, you square this input plus you double the input plus 3. That's the idea of composite function, okay? So again, composite function is a function where the input becomes functions. So like this, x minus 2 is a linear function, right? So then we've only seen a case where it's linear, right? And can it be something else like quadratic or like log, exponential, or anything else? Yes, why not? Let's say the input is x squared plus 1. Then again, the function fx means whatever input you have, you add 1. Then whatever input you have, which is x squared plus 1, you add 1, which yields x squared plus 2. And for, let's say, if you want to put something like sine x plus cosine x as the input, then what does that mean? For this particular input, you square it, and then you multiply it by 2, and you add 3. Okay, so that's the idea of composite function. All right. One thing to know that not every functions can have composite functions. So before I go for this, I'll quickly tell you some notations for composite functions. So we write composite function like this. So we call this as f of gx, which is equivalent to say that gx becomes the input of f. So for this case, if we want to use this, that means fx is x plus 1, and we call gx as x squared plus 1, then f of g, using this definition of functions, f of gx equals to f gx as an input, and gx is x squared plus 1, so x squared plus 1. So this is how we can use the notation for composite function to write it, okay? So that's the basic notation, and I'll tell you a bit more about the algorithm of composite functions so that you can tell whether a composite function exists or not, because for some particular cases, the composite function is not defined. For what case? Let's say, for example, this. So something like this, or f of g or g of f. So f of g means we put gx as an input for fx, right? And g of f, that means we put fx as an input for gx. So let's do one by one. Okay, so first let's see f of gx. So note that fx is a function and gx is also a function. That means fx has its own domain and range, and it's the same for gx. Gx has its own domain and range too. So first, gx must have its own domain and range. And what's the domain for gx? So gx is root x. So as we've seen for the domain and range of different functions, so it's an irrational function where k is a positive constant, 1. So x, the domain, is equal or greater than 0, and y is equal or greater than 0. Then what about the range and domain and range of fx? fx has its own domain and range too, right? And the domain of fx is all real number. And the range of fx is also all real number, right? And note that we are putting this inside this. And we see that first we have an input, we have an x value, right? And we put that into gx. Then we will have a certain output, right? And then we note that for that output, so the output of gx, we put that into the input for fx, right? And then we evaluate the y value. That's how it works. Then for this case, does f of g exist? That means, can we find every f of g for the domain? The answer is yes. Why? Because x is greater or equal to 0, right? So we have all possible values of y, right? But for this value, we put it here. And note that this y and x are just dummy variables. So it doesn't mean by y cannot be x. No. So it's just the set, right? That means it's just having a set of numbers from 0 to positive infinity. And we're trying to fit that into all real number plane. So y greater or equal to 0, then if we have 0 here, we're looking for this region, and then we are trying to see whether this fits into, there's no boundary, so into the entire region. Does that fit? And the answer is yes, because this set is certainly bigger than this. This contains every point here, right? So that means the domain is defined so that we can find for range. So this one, it exists because we can simply put this set into this set. Okay, so again, don't get confused with the use of y and x. Y and x are just dummy variables. It does not contain any meaning. So here, what it's trying to say is that the output for gx is numbers that is greater or equal to 0, like this. And this, the domain of fx, here, x belongs to real number. That means it's the set of every real number. So this. So x and y doesn't have any meaning, okay? So we try to see whether this fits into this. And why are we looking for this range fitting, whether this range fits into the domain of f? Because as you can see from the algorithm, we first have the domain for x, gx, right? So with the input, so from the input, we put it into g, right? And we evaluate for that particular value for g, I mean the output for g. And we put that in again into f. That's the way how composite function works. So for example, here, for this case, f of g, so gx is root x, so that means we're looking for f root x, right? So fx is x plus 1, so for every input we add 1. That means for every input, root x, we add 1. And let's try to evaluate when x equals to 1. Then when fx equals to 1, so here, what we are trying to do is that first, that x goes into g, right? Like this algorithm. So we have an input where x equals to 1. So the input is 1. So we put that input into function g first, right? And then we have the output for g where it equals to 1, right? Root 1 is 1. And then with that result, we put that output of g to fx. So we have f1. That's why we have 1 plus 1 equals to 2. That's the algorithm of composite function, okay? But what about for g of, so for this one, it exists, right? Because it can contain every value of gx. Then what about g of f? Does that exist? So let's see whether it exists or not. Doing the same thing here. So okay, I don't have much space, but so doing the same thing. Now fx is the input function, right? So fx has its own domain and range, right? So since it's a linear, x can be anything and y can be anything, right? Then what about gx? It's simple, right? Because we've already done it. So the domain of gx is greater or equal to 0, and the range of gx is also greater or equal to 0. And let's see whether f of g exists. So doing the same thing as what we did. So first, we have the input in f, right? So with that input, we put it into f, and we have the output of f. And with that output, we put that output of f as an input of g. And then we have the output for g eventually. And let's see whether this works, and in fact, this does not exist. Why? So first, what does this mean? It means it can be anything, right? So what this is trying to say is that for the given input, y can be anything, right? I mean, for the given domain, y can be the range, the output can be anything. So that means fx has set of all real number as an output. But what about the domain of g? Domain of g can only be greater or equal to 0. Does that fit in? For this one, yes. But for this one, no. Because gx can only be defined when x is greater or equal to 0. But what this means is that from fx, we may have negative value as an output of f, right? So for example, when x equals to something like -2, let's say, then the output of f must be -1. That means that -1, which was the output of f, goes as an input for g. Then we're trying to evaluate g -1, but does that make sense? No, because g -1 is root -1. And again, function for IB, we only define for real number cases. So we don't worry about negative number. That means it does not exist. So for this one, the function does not exist. Okay, so you have to check whether the output of the inner function fits in to the domain, the input of the outer function. Okay, so here it does not fit in, so does not exist, DNE, and this one it exists. Okay, so that's how we can find whether a composite function exists or not. And that's already on hour, but we still have inverse function to do. Oh, okay, it's gonna be a bit long lesson, but yeah, let's try to finish off till inverse. But one thing, for composite function, so it involves some algebra as well, because so if we have fx defined and gx defined, then it's very easy to find f of g, right? Again, just put g into f and we can do it. We know how to do it, right? But what if you have f of gx equals to ln k, let's say, and gx equals to, let's say, e to k, and find fx. So this is a bit difficult question, so I'll try with easier one. So let's say f of gx equals to x squared plus 5, let's say, and let's say gx equals to 3x plus 7, let's say, and gx equals to x plus 2, and find fx. Then for this one, the reason why this is simple is because you can solve this by inspection. How? So note that remember, gx is the input function, so gx is already defined, right? So it's x plus 2. So what this means is that if we put x plus 2 as the input, we did certain operation to make it into 3x plus 7. Then we can try to make x plus 2 from here. And how? So that's 3x, and then we can split 7 into 6 plus 1. Then if we factorize this by 3, then we have x plus 2 plus 1. So we see that, oh, the input is here. So that means fx equals to 3x plus 1, right? Because that's why, so for every input, we multiply by 3 and we add 1. That's why if the input is x plus 2, if we put that into function fx, then we multiply x plus 2, which is the input, and then we add 1, which we have that, and then going backward, we have this. So this, we can solve it by inspection. But something like this question 1 is the case where inspection is not easy to you can't really apply inspection to solve. So if you're clever enough to solve this by inspection, I mean, you can still solve it if you know the exponential and log properties very well. So for this one, if you want to solve this by inspection, it's simply just so fx is ln natural log x, right? Because so here, when we put e to k as an input, that means we take natural log and we take natural log again into the input, right? So what does that mean? That's k, right? So ln k. So that's how we do it. But again, it's difficult to apply inspection to solve this. So then how can we do this without using inspection? So we recall what we have done so far when we had something unfamiliar. So we want to find fx, right? We want to find fx given this. But we have f e to k inside, right? Then let's say e to k be x, right? Then fx equals to ln k. But here we have a problem. The function is in terms of x, right? I mean, that means the input is x, right? But how can the outcome be k? So that means, why don't we try to rearrange k in terms of x? And how do we do that? K in terms of x. Then we take natural log on both sides, or you can just rearrange this into log form so that we have k equals ln x, right? That means we substitute this, k is ln x, that means ln x. Done, right? So we can use this substitution method to solve it. And for example, if you resist to use substitution, and if you think you're clever enough to solve by inspection, then I'll give you a question where it's almost impossible to solve using inspection. Something like this. So this is again a composite function, example of a composite function, because this is the input, right? Input function, and f is the outer function. So we have this as an output. So it's f of g, where g is this. If you try to solve this by inspection, then I'll admit that you're a very, very clever student, but I'm pretty sure almost everyone cannot solve this by inspection. So let's just use substitution, because substitution, it takes a bit time, but at least you can solve every question like this. So again, let x plus 1 over x minus 1 be k, let's say. then fk equals to x plus 2 over x minus 2. So again, the input is in k, but the function is in x, right? So it doesn't make sense, right? If the input is k, then the output must be in k as well. So what we can try is that we can try to rearrange x in terms of k. And how do we do that? Well, it's not that hard. So x, rearrange this, 1 plus k equals to kx minus x. So so x equals to 1 plus k over k minus 1. Put them back. 1 plus k over k minus 1 plus 2 over 1 plus k over k minus 1 minus 2. Okay, I know that for SL students, you're not really familiar with handling like equations in fraction form, but don't treat it hard, because if you don't want to make it like that, what you can try to do is that you can make it like this, because that's the definition of fraction, right? Something divided by something, right? So we can use this. So first, common denominator. Right, then if we solve this, we have this, and we have this. And division, what do? We flip it, right? Cancel, so eventually we have this. So for every input we have that, then we can just replace k by x, right? Because input can be anything, right? Done. That's how we solve it, okay? So try to practice some of this. So you can practice with inspection, but yeah, try to use substitution as well to solve it, okay? Substitution is a very good method. All right, so we are almost the end. So it's already around, what, 80 minutes? So I understand. I'm trying to finish the entire basic function in SL syllabus in a lesson. So that's why it's taking a bit long. But after this, you're done with basic function. You're only left with some transformation. But unfortunately, if you're in SL, you have to do a bit more. So last, inverse function. So inverse function is also a function, right? So as I said, every function has an algorithm, right? So we have input, and we have a function, and we have the output, right? Then what's an inverse function? So inverse function is a function where the input becomes the output. And many of you may get confused with the meaning of this. So don't treat it hard. I'll give you a very clear example. So for example, let's say for example, all right, so you want to encrypt a message. So you have devised a function where you reverse the order of a message. So your input, let's say, is high. So if you put that into the reversing function, then the output will be IH. So that IH will be the encrypted message, right? Then if you want to decrypt that message, that encrypted message, then we can try to find the function that reverses what you did. So for that one, so it will be the same function, right? So reverse IH, right? Then reverse it again, it reverses again, so it's high. So we can decrypt the message. But for example, what if we have something like this? So for something like this. So you have devised a function where it replaces every first letter to k. So for example, let's say your input, so this is a function, and your input is let's say how are you, let's say. Then I said for every first letter we change to k, right? So then the output can be cow, cray, co, right? Then what we are trying to do using the inverse function is that given you have this encrypted message, you want to devise an inverse function to find out the input. So input becomes the output, and your aim to find the input, the original input. Okay, that's the purpose of inverse function. Then how do we do that? So it's not as simple as you think. So we have to make this into some we have to see case by case. So for example, linear, quadratic, and so on and so on. So before that, I'm going to talk about a bit of more properties. So one thing that you have to be aware is that if you have an original function, and if you have found the inverse function, then as I said, if it's a function, then we have an output, input and output, right? And I said that inverse function is a function where the input becomes the output. But what output? Output of the original function. So note that for most of the cases, the original function and the inverse function will have different equation. And if they are the same, then we call that as self-inverse function, which if you're in SL, you don't really have to know, but for HL, you have to know. And an example is 1 over x, but I'll tell you why later. But anyway, so as I said, input of the inverse function becomes the output of the original function. So that means this becomes the input, and that becomes the output. Okay, so then let's see. So and one more thing, the most important thing. So remember that in the beginning of the lesson we have seen two tests, right? Vertical line test and horizontal line test. And vertical line test is to justify whether a graph is an equation is a function or not using the graph. And horizontal line test, as I said, it's used to find whether a function is 1-to-1, right? And note that only 1-to-1 functions have inverse. But one more thing is that if you want to be very precise, then to be honest, it's not just 1-to-1. It should be 1-to-1 corresponding functions have inverse. So the reason why we have to put you don't have to put corresponding for if you're in IB, is because you don't learn the concept of codomain. So if you learn set theory for HL option, then you will not have domain and range. Instead, you have domain and codomain. And codomain is a bigger set of range. So range is a subset of codomain, but if you're not gonna take that, then don't worry about it. So you can just use one-to-one, but just if you want to be precise, then use this term. And why do we, and I have made 3 stars here, right? Because you have to use this term to explain whether a function has an inverse or not in your exam. So in your final exam, IB final exam, the question may explicitly ask you to explain why a certain equation has an inverse. And you can explain it by using this term, one-to-one corresponding. And also, in order to justify whether a function is one-to-one, you can use horizontal line test to explain, okay? So yeah, so that's the case where we have an inverse function. Now, I said the domain of the original becomes the range of the inverse, and the range of the original becomes the domain of the inverse. So that means if we have x and y, that means it becomes y and x, right? So we can, so this, using this idea, if we make that into, if we imagine this graphically, that means the original function and inverse function is always reflexive over y equals x. So I'll give you an okay, so we have a good example here, log and exponential. So as I mentioned in the beginning, log function and exponential functions are inverse to each other. What does that mean? That means one thing. So in order to be inverse function, I said it has to be one-to-one, right? And in fact, this is one-to-one, right? It passes horizontal line test. Note that for this one, it's not entirely, like, it doesn't have the same value for different values of x, right? It's just decreasing. It's getting smaller and smaller. So smaller, smaller, smaller. So very negligible change, but still there exists a change. They're not the same thing, okay? So this is one-to-one. And this, is this one-to-one? The answer is no, right? That's why it does not have an inverse. And again, this is one-to-one, so we have the thing here. And also note that in inverse function, I repeat again, so the original function's output becomes the input of the inverse function. And let's see. So in exponential function, so the domain is all real number, right? And we see that the range of the inverse becomes the real number. So x here, the domain becomes the range, right? Domain becomes a range. Domain becomes a range. And same thing, range becomes the domain. Range becomes the domain. Okay? So we can get the domain and range of inverse functions using the original function, or we can also find the original function's domain and range using the inverse function, okay? Then the very important thing is first, sketching. I'll talk about sketching first, and then I'll tell you how to find the inverse functions. So as I said, the graph of inverse function and the original function, they are reflexive over y equals x. And y equals x is called the identity function. So when I sketched the graphs of log like this, I told you that it's not really easy to sketch this directly without knowing the log, I mean the inverse property. So we are trying to sketch this using the inverse property now. So I'm very sure you're all fine with sketching exponential. If you have any problem, then that's problematic, okay? You shouldn't have any mistake, any problem with this. So this is the case where the base is between 0 and 1. And that's the exponential graph, right? So we have the horizontal asymptotes, y equals to 0, right? Then, as I said, everything is reflexive over y equals to x. So, okay, I'll use my expensive pen. So we have y equals x like this. And again, everything is reflexive, right? Then y equals, so every y value becomes x. And every x values becomes y. So we had y equals 0, right? Then in the inverse, we have x equals to 0. And what about the graph? So we see that from negative, positive, it's in this direction, right? And x was negative and y was positive. Then x and y switch, right? So y becomes negative and x becomes positive. And that's how it looks like. And here, x is positive, y is positive, so we still use this region. So that's how we could sketch. And also, this intercept is 0, 1, right? And this is 1, 0. So let's say this is the point A. Then this point B is the image of A. So you're basically sending this point into inverse, and we call that as image, right? Image, okay? So that's the basic sketching. And so let's quickly see some cases where the inverse is not defined, and let's find the reason why using the sketch. So we have a very simple quadratic equation, okay? One thing, so quadratic functions, they pass vertical line tests, right? But they don't pass the horizontal line test because it's many to one, right? So many to one, it can be a function. So, but it's not one to one, right? So that means this should not have an inverse. And let's see why. So again, how we sketch the inverse. So note that we can sketch the inverse, right? But just the fact that it's not a function. So remember when we, in the very beginning, so this is still a graph. It's a graph of a certain equation, but just the fact that it's not a function. So the same, this one, so the inverse of quadratic function does not exist, but we can still find the equation and we can still find the graph of it. And in fact, the graph looks like this. Okay, so please be note that it's not to scale. So it's just reflexive over y equals x. So we see that for every x value here, we have two y values. So it's one to many, so it's not a function. One tip to sketch the inverse easily. So like all these examples that we've seen are very simple. But what if we have something like this? It may be a bit difficult to sketch, right? So what you can do is that you can point and you can find some important points. So for example, the local maximum and local minimum. So you can find these using your calculator, graphical display calculator, or you can use calculus later, so differentiation, to find these 2 points. But yeah, so there are many ways to find these points. So first find those points, and then you can send the image. So remember, so for example, if this is let's say 1 and 1, and let's say this is -1 and 2, for example. Then in the inverse, let's not call this as 1 and 1, let's say 2 and 1. Then in the inverse, this point will be 1 and 2, and this point will be 2 2 and negative 1. And remember, these two are the image of these two original points, right? And so, and also this, let's say negative 2 and 0, then 0, negative 2. So what we can do is that we can plot all these points and then connect them back. So so it's a rough sketch, but it will look like this. And more easy thing that you can try is that, so remember I said x and y changes, right, for inverse. Then that's the original function, right, x and y. So this x-axis becomes y-axis, and this y-axis becomes the x-axis. So you just sketch the original curve like that, okay? That's how you can sketch the inverse. Oh. One last, no, not the final. So, okay, it's a very long. It's gonna be a very long video. So very important thing, especially for HO students as well. So if you have to find the intersection between the original function and its inverse, or let's say original equation, because it doesn't have to be function, to be honest. So how do we find the so if we have to find the intersection, then what did we do? We have to equate the equations and then solve it like how you find the roots, right? How you find the roots. But for this case, sometimes it's very difficult to find the equation of the inverse. So before I tell you how to find the equation of the inverse, I'm going to tell you how we can find the intersection without finding the inverse. So intersection means when the graph meets, so intersect each other, right? Then is, so for example, let's use this example as well. So for this one, imagine that these are at the same time, same graph, so it will look like something like that, right? This is what it looks like. Then we see that there are two intersections, and let's say this, let's just as an example, I'm sorry, I'll just use another example. Let's say we have x cubed plus x plus 1 as a function, okay? So you can use GDC to find the roots, but let's say, so there must be a root between -1 to 0. So I don't know the exact root for this because I'm not bothered to find it. And there must be only one real root, so that means there are two non-real roots. So cubic function looks like that. So this is how it looks like. It's a very rough sketch, okay? So that means if we want to find the intersection between its inverse, then if we sketch the inverse, it will look like this. Yeah, so this is how it will look like. Then, okay, actually, in fact, it will look like this. So this is how it looks like. Then, in order to find the inverse, I mean the intersection of this, so this intersection, what we can think is that as what we did so far, we have to find the equation of the inverse and then equate them, right? But unfortunately, we don't have the inverse. I mean, we can't find the inverse. One thing, you cannot find the inverse for this. Then what can we do? So note that inverse and the original function is reflexive over y equals to x. Oh, and sorry, I forgot to tell you that the notation for the inverse is f. So we write it like that, and this is not the same as reciprocal. So inverse is not the same as reciprocal. Okay, this is 1 over fx, but this is inverse. But anyway, so let's come back. So we know that the inverse and the original function is reflexive over y equals to x, and we see that this intersection y equals to x also passes through. Then what does that mean? You don't need to know the equation of the inverse. You just need to equate with y equals x. So x cubed plus x plus 1 equals to x. So x cancels out. So x cubed plus 1 equals to 0. That means x equals to negative 1. So at negative 1, it has the inverse. So the inverse, the intersection point, so at x equals to negative 1, we have the intersection. And the full coordinate of the intersection is negative 1. So this is how we can find the intersection, okay? Alright, very last thing. We're done. After this we're done. So, okay, it's gonna be a 2-hour lecture. So I recommend you to take some break to watch this. So finding the equation of inverse. So I'll tell you some steps. So you will have a function fx, right? And remember, in the inverse function, x and y just switch, right? Then you write x in terms of fy. I mean, just replace all x by y and all y by x. And second, write the equation y in terms of x. So rearrange the equation in terms of x. Then you're done with finding the inverse. So it looks like very simple, right? So let's try. We always start with linear. Very simple, right? So linear, let's say mx plus c, right? So using the first step, we switch x and y. So x equals to my plus c. And rearrange the equation in terms of x. Then it's also very simple, right? Because x minus c over m equals to y, right? So that means the inverse equals to x minus c over m. Okay? But what about quadratic? So quadratic is something where it gets a bit more complicated, just a bit. So I'm not gonna use a general quadratic formula because if I introduce too many variables, it will be more confusing. So I'll give you an example. So something like let's say we have an equation like this, okay? Then, so y equals to this. Then, again, just replace all x by y and all y by x. So that means using the first step, x equals to 3y squared plus 7y plus 1. Now, the first step is simple, but the second step is a bit problematic because it's not really easy to write y in terms of x only, right? Because there are two terms involving y. So what we can do is that we can complete the square. Alright, I made the equation a bit nasty, please understand, but this will be something you will get for most of the time. So if we complete the square, we have it like this. Then we can write y in terms of x. How? So move this constant here and divide the entire thing. So, and we have 3 here, right? Divide everything by 3. And square root both sides. Remember, when we square root both sides, we have plus and minus. Don't forget to write plus and minus, okay? It's not just square root, it's plus minus square root. And we remove this to the other side. Not remove, we move this to the other side. Then that's it. That's the equation of the inverse. So we have two equations. That's why this is one-to-many, because for one value of x, we have two values of y. So it's a one-to-many function. That's why for this one, it does not have an inverse function, but still we have an equation of the inverse, okay? So please be clear with equation and functions, okay? Equation is just an equation, equality. Function, again, in mathematics, it has to be either one-to-one or many-to-one, okay? So that's how we find the equation of the linear and quadratic. And if you want to expand this furthermore into trigonometry or log and exponential, rational should be very simple, and irrational is also very simple. But yeah, so for SL and IGCSE, this should be it. And for SL, if you want to do a bit further, not required. So for trig, if it's y equals sine x, then the okay, I'll use the proper notation. So fx equals to sine x, then f inverse is simply inverse sine, which is arc sine, right? And if it's cosine, then the inverse is arc cosine. And lastly, if x, the original function, is tangent, then f inverse is arc tangent. Okay? So one last thing. One of the property for inverse we have covered almost every property. So inverse function is a one-to-one only one-to-one corresponding functions have inverse function. And also with intersection, we can equate the equation of the original and equation of the inverse together to find the intersection points, right? Sorry. In order to find the intersection point, we can equate the original equation with y equals x or the inverse equation with y equals x. So you can just use whatever you're given with, okay? One last property of inverse is that if you compose the original and inverse, you just have x. And similarly, if you have inverse with original composed like this, you have this. What this means is that, for example, if you have fx as e to sine cosine tangent x to 7, let's say, then if you want to find f inverse of fx, what is it? You don't even have to calculate it, it's x, right? And the same for something like this, so it's the same for this, this, okay? Then something, you may also have something like that, so something like this. So what if you're asked to evaluate this? Again, don't panic, these two cancel, okay? Then where can we find this? So in log property, one of the log property which HO students learn, so for if you're in SL, it's a good thing to know as well. So if we have a to power of log base ax, we have x. And similarly, if we have log base a and a to x, we also have x. And this one, SL students also did it, but this is for H only. And why do we have these results? Because if we let fx as a to x, then as I said, exponential and log, they're in inverse property, inverse relationship, right? Then what this means is simply you composed f and f inverse, right? Because in the original function f, you put the inverse function, which is f of log base ax. And what's fx? A to x, right? So for every input, we make it to the power where the base is a. So same, a base is a, and that becomes the power. And that, according to the log property, we have x. Okay, so that's how we derive this formula. And for this one, we can also use log property where you can remove this power outside as a coefficient. And if the base and the inner value of log is the same, then it's 1, so it leaves x. But we can also use this. So this case, it's f inverse of f, right? Because in the inverse function, fx becomes the input. So f inverse a to x. And what's f inverse? That means log base ax, right? So for every input, we make it into log. Put it into log. So the input here is a to x, so we put it into this log, so we have x. That's how we can solve it, okay? So that's it for today. I understand that this video is quite long, but for SL students and IGCSE students, you're done with basic functions. So now what you're left with is just some transformation and some sketching methods, okay? But if you're in HO, what you have to do further is that you have to do some higher order functions. So we only looked for quadratic, right? But some cubic and higher order, but it will not be difficult. But in composite function and inverse function, you must learn domain restriction. So we have seen some cases where the composite function or inverse function does not exist, right? Then we can try to restrict the domain to make them exist. And I will talk about that in the next video. And SL students or IGCSE students, see you in the later videos in transformation. So bye.